Hi, in this exercise we will be dealing with 2D frames. So to help me doing this problem, I selected this exercise, which is a simple frame, but this frame, it has an inclined element and also a triangular load. So this will help us go into a little bit more complex features in SAP2000. So what we need to show here is the joint displacements, support reactions, print the shear moment diagrams, and print the deflected shape. All right, so let's jump right back to SAP, create a new file. I will be using the grid only again, but you can select the 2D frames to help you. And here we have to select the number of grid lines, grid spacing, like we did for the last one. And going back to our problem, the horizontal direction is going to be our X direction and the vertical is going to be our Z direction, just like I explained in last exercise. So in the horizontal direction, our X direction, we need 1, 2, and 3 grid lines. So let's select 3 grid lines. And in the Z direction, we need 1, 2. So let's select 2. This time, let's use only 1 grid lines in the Y direction. And here in spacing, like I told you last video, it needs to be an equally spaced grid. So if you look at our problem, we don't have an equally spaced between the grid lines. But let's select 6 meters as the grid spacing, and then afterwards we will edit this value to match our problem. So let's select 6,000 as it is right here already. We don't care about this direction. And our Z direction is going to be 4.8 meters. So we can come and 4.8 meters. Let's select the XZ view and right click on the grid lines. And here you can see that the first grid line in the X direction is at 0, so here. The second one is at 6,000 and the third one is at 12,000. But we want the third one to be 2 meters away from the second one. So we can normally come here and edit to 8,000. Here is our new grid. So selecting the full view. Now, before we draw our elements, we need to define our material properties and our sections. Going back to our problem, we see that our material has to have a 28 GPa modulus of elasticity, an area of 110,000 millimeters square, and an inertia of 680 10 to the power of 6 millimeters to the fourth. So first, let's create our material. Let's use this predefined steel that comes with SAP. Let's delete the concrete. Use this, modify. Let's rename it to steel or just material because we don't know if this is steel or not. Our module of elasticity in newtons by millimeter, it's set to almost 200,000 MPa, and we need only 28,000 MPa. So 28,000 MPa, and that's it. That's the only thing we care about now. Click OK, and then we have our material set up. Now we need to define our cross section. So as I showed in the previous example, come to the frame properties, add a new property. To be easier, let's just come to the section designer, call this section. And the base material is going to be the material we just created. And then let's edit this. The easiest way is just to create a rectangle. Now, to create an area of 110,000 millimeters square on a square cross section, we need to have sides of our cross section of 331.66 millimeters. 331.66. Let's select the material that we just created. Press OK. With the full view, come to display to show the properties. And here we see that our area is close enough to 110,000 millimeters square. Now, another thing we need to satisfy in this problem is the moment of inertia of our cross section. Right here, we see that our moment of inertia is 1008 to the power of 6 millimeter to the fourth. And we need 680 to the power of 6 times 10 to the power of 6 millimeter fourth. So the way I'm going to do it is a easier way, but if you know a cross-section type and the dimensions of that cross-section type, that will give you both area and inertia that you need for this problem, you can also use it in the section designer. But what I'm going to do is that I'm going to click done here. I'm going to come to the property modifiers, and I'm going to modify the moment of inertia about both axes by the factor that will scale down our moment of inertia from the value we have of 1008 to the value of 680 that we need. And that value, that multiplier, is 0.675. And since we have the equal moment of inertia on both axes, I'm just going to multiply by the same factor. So now I click OK. Click OK. And then we have defined our section and our material. Now we can simply draw our frame. I don't need to explain it anymore since it's the same process as the previous video. The only difference is that now the moment release is set to continuous instead of pinned, because I want that moment distribution occurs between the elements. In here, I'm going to draw from left to right, starting here on this grid point and finishing here. And this will allow me to have the same number nodes as our problem, also element numbers in this problem. So I'm just going to come here, draw this, press Ask to finish. And then we have our structure. The next thing that we need to do is to put our support conditions. So back to our problem, we see that in node 1 and 3, we have a fixed support condition, and at node 2, we have a roller. So coming back to SAP, selecting nodes 1 and 3, if you want to see if that's the real nodes numbers that I have, you can go there and select the node labels. You see, so selecting nodes 1 and 3, coming to assign joint restraints. I'm going to select the fixed, click OK. And in the second, I'm going to select a roller, which basically just restrains the vertical direction. So I'm going to come here, unselect everything except for the vertical direction. So here you see we have fix, and node. So one important thing to keep in mind is to always save your problems multiple times as you're doing it, so you don't lose any progress. So right here, I'm going to save it. I'm going to call it video 3 example. Click save. And the only thing there's left for us to do is to define the loads that we have in this problem and run the analysis. So the first thing we need to do before assigning the loads to the element is to create a load pattern that is not the dead load. So I'm going to create a live load pattern, select live, click add new load pattern, set OK. And now we can assign the loads to our elements. So the first element here has a 12.5 kilonewtons per meter load applied on the element. So I'm going to come back, select this element, come to assign frame loads and select distributed. In here, I'm going to assign a load to the live load pattern. And in here, you can see that you can specify a trapezoidal load based on points along the element's length, or you can just specify a constant uniform load along the entire element. So I'm going to come here and specify 12.5 newtons per millimeter, which is the same as kilonewtons per meter. So I'm going to set OK. And here we can see our distributed load applied in the right direction, which is the vertical pointing down. And we can see the value of 12.50. Now, to assign the load to the inclined element, we can see here that it starts at 12.5 at this end of the element, And when it comes to 1.2, it goes to 0, and then from this here on, there's no load applied. This is to simulate, as you can see here, if this element is underwater. So remember, from fluid mechanics, the pressure of the water grows in a triangular shape as the depth of the element increases. So the way we're going to apply that in SAP2000 is using the trapezoidal function of the distributed load. But first, we need to define what is this length that has no applied load, because we will need this to set the points in SAP2000. So I have this element, this document over here. So this is my element that has 2 meters horizontal, 4.8 meters vertical, as the same as the problem that we have. And we went first to figure out the L total, the length, total length of the element. And then we need to define this length over here, because in SAP2000, we're going to specify 12,000 kilonewtons per meter at this end. And we need to know at what distance in the element this load is going to come to 0. So for that, we first need to define the horizontal length here that corresponds to 1.2. And then from this, we can define the length of this end of the element. And the L total, we can just define using the values we already know. So I have here the calculations that I did. We're using just basically triangles. And here I already have the calculated values substituted on the figure. So let's go back to SAP, select the element we want, assign frame loads distributed again, but now instead of using the uniform load, I'm going to use these trapezoidal loads over here. So these trapezoidal loads divide the load in 4 points over the element's length. So because I draw the element from node 2 to 3, node 1.1 will be, if it's at 0, it will be here. And if node 4, which is at 1, it's going to be at node 3. So right here, I know that at this point over here, I have a load of 12.5. But keep in mind that it is applying in the coordinate system global and the direction of gravity. So the coordinate system global, it's this one we see over here, X, Z, and then the Y over here. So when you see global in gravity, it's applying vertically down, such as this one we have over here. And in our problem, we have a load that is in the element perpendicular to the element length. So we need to switch in SAP2000 the coordinate systems from global to local. And now we have to define in which direction is going to be applied. Like I told in the previous exercise, the first direction is the element length, along the element length. The second direction is perpendicular to the element length. And the third direction is perpendicular to the second. So in this case, we want to apply in the second local direction, negative, because we want to point in towards the element. And now point 0 is going to have minus 12.5. And now, since we have a triangular going down, we just need to know at which relative distance the second point is going to be. So if you come back to our calculations, 5.2 minus 1.3 is equal to 3.9, which is exactly 75% of the entire length. So we can come back here and set that at 75% of the entire length of the element, this load, which started at minus 12.5, needs to go back to 0. We don't need to care about any of these other points over here, because only point 1 and 2 already fully defines our load pattern. So let's click OK. And here we can see that our load is applied correctly. So let's save again. And before we analyze, you come to set analysis option, select the XZ plane, which is the plane we're drawing our structure, to unselect the degrees of freedom, we don't care. And let's run our analysis. Again, let's unselect the modal and the dead load analysis. Just run the live load, press run now. And here SAP2000 shows us the deflected shape. One thing we can do to see the deflections of each node is to simply put our mouse over the nodes, and SAP will show a list of the displacements of that node. Because node 1 and 3 are fixed, all the possible displacements needs to be 0. But this node over here, you can see that it has displacement in the X direction and rotation in the Y direction. So our first deliverable, coming back to our problem, is to show a joint displacement table. Now this is the same as the previous example where I show you how to come here to display show tables, analysis result, joint output, and then displacements. Clicking OK. Select everything we want. Go back to an Excel file, for example. Paste the joint numbers, the X displacement, the Y displacement, and the rotation. So this you should already know how to do based on our previous video. Our second deliverable is a support reaction table. So let's go back to our SAP2000. And because we need the units of this information in kilonewtons and kilonewton meter, let's change our SAP2000 units to kilonewton meter before we go to the table again. Come to the table and select reactions instead of displacements this time. And we will have our information in kilonewtons and kilonewtons meters. Just come to Excel, paste, get the joints, get the X reaction, the Y reaction, which in this case is the Z in SAP2000, and the moment. And that's it. So our third deliverable is to print the shear moment diagrams showing the peak values on the diagrams. So to show the shear moment diagrams, as I explained in the previous video, you can come to this icon over here, select frames, cables, or tendons, or come to display and show forces, stresses, and then frames, cables, and tendons. And here we can select both shear 2.2 and moment 3.3 to see. The shear 2.2 is selected and not shear 3.3, as well as moment 3.3 and not moment 2.2, because these are the shear moment diagrams in the coordinate systems we draw our structure, which is X and Z. So if we want to see the shear diagram, we come to here, select shear 2.2, and here we can see our shear diagram along the element length. We can do the same for the moment. But here, to see the values, you have to hover your mouse over the element to see specific values. So to show the values on the diagram, come back to this window and select Show Values on Diagram on the very bottom. Click OK. And here you can see the maximum values of your moment diagram, also for the shear diagram. It might be a little bit hard to see, so you can zoom in to get a better view, or you can come here and select just what you want. You can get rid of the nodes, labels to be easier to read in here, and copy and paste this window. So another thing you can do to easily see the results of moment shear, axial torsion, or whatever other forces you have on your elements is to, having a diagram being shown on the screen, right click the element and you will see this screen where you can see detailed information about the shear, moment, deflection, and the load condition of the element. You can click on any point you want to see specific values of that point. You can also come here and type a specific point that you want, and it will show you all this information for the point you selected. You can also click in Show Max to see the maximum values of each of this information here. Let's press Done. And before we do that, I want just to explain these stations that we talked about in the last video. In that video, when I show you this, when I talked about the stations, all the values of the axial forces were the same for all stations. But that was because that was a truss, so the only force in the element was an axial force, which was constant throughout the entire element. In here, for example, we see that our shear diagram and our moment diagram are not constant along the element's length. So you can see that at each station, shown here by these very thin white lines, every station will have a different value of shear and a different value of moment. So stations help you better view or better understand the distribution of moment and shear, also deflections, throughout the length of the element. Last thing you need to deliver is the deflected shape. For that, simply come to Display, Deflected, Deform Shape, select the load combination Lombo case to live, click OK. Or you can come here and select Show Deform Shape. It's the same window appears, click OK. And here you have it. So you can just copy and paste it on your assignment sheet. That's it for this video. And I hope this helps you in your assignment, and good luck.